Hello again to everybody. I'm Rufat, and today I'll be talking about the energy industry and how it's related to oil and gas and what the future will be looking like. So, agenda for today is I'll introduce myself and we'll talk about the history of energy. We'll talk about the present state of affairs, and then we'll discuss what the future options are. And then I will specifically talk a little bit more about hydrogen because this is one of my favorite topics, but there are a lot of other ways that other pathways into low carbon future. If we have time, maybe we'll discuss more about that. And in summary, we'll have open discussions and we'll share ideas um, um, about the energy and oil and gas industry. So this is not I didn't design it to be like a university lecture type of thing where I would just go through the slides and read out and you. So my intention is to have open discussions. So if you have ever questions, please feel free to raise them as we speak. Don't have to wait till the end to bring your questions. And if there's anything not clear in the slide, so I didn't put a lot of text in the slide, so I'm planning to do the speaking myself. So if you have any questions or if there's any information or chart or graph unclear in the text, please let me know. Okay, so brief information about myself. I think you've probably already um, uh, introduced to me. I am a chemical engineer and I've been working for more than 10 years in this industry. Majority of my career, I worked as a engineer for BP, process engineer for BP. Right now I'm working for SOCAR KBR, a joint venture between KBR and SOCAR. And we are basically, I think, one of the biggest energy engineering company in the country. We are delivering probably the country's biggest projects, multiple offshore platforms, onshore terminals. We are carrying out a lot of concept studies for the future projects. And my aspiration is that hopefully in the future, Azerbaijan will be able to engineer and design its own projects from ground up without any need for external expertise from other countries and other companies. Actually, when we talk about oil, oil was most people think the common understanding of oil industry history leads us to USA early 19th century, but in fact there are much older players than US in oil game, and the most ancient oil producer in the world are ancient Chinese. So you can see from the right hand screen, so right hand picture is it's basically the replication of the ancient drilling technique with bamboo drill bits in the 19th century, but this is probably the same setup that were used by ancient Chinese more than 2000 years ago. And on the left-hand side, you can see something that looks like a roller coaster, but it's actually um, a system of pipelines with supports, which is made of bamboo. It's known to be more than 2000 years old, this technique of transporting fluids with bamboo pipelines. So one of the, it's worth to note that the first usage for oil has not been for energy. It was used for other purposes as a medicine, as a construction material, and so on. But Chinese were also the first to use fossil oil as a source of fuel, and they needed the fuel to produce salt, because salt was produced from the salty water, similar to actually what we produce in Azerbaijan in Tuzlu Göl. were extracting quite salty water and applying energy heat to evaporate water and extract the salt. The similar technique was used by ancient Chinese, and they used oil to burn and take energy for evaporation of salt, water from salt. Then there are multiple places. Oil was found in multiple places in across different continents, and one of the earliest players were Azerbaijan. Um, so we have records of oil production around Absheron Peninsula that dates back to 9th century from multiple sources. But this was, minor extractions because before the Industrial Revolution, the demand for oil was not great, but Azerbaijan already had uh, oil extraction and production in place. So the real turning point was in the middle of 19th century when we started extracting oil with more modern to that time tools. So before that, it used to be all hand dug with shovels and manual labor. In the 19th century, people started applying more modern techniques and machinery in drilling for oil. And you can see from the left-hand side picture, you can see this is somewhere near Balakhane, oil wells, and in front you can see something like water. It's actually open oil reservoirs. So they would produce the oil and they would store it on the ground. So they didn't have, for example, tanks at that times, and obviously safety and environment was not much consideration during that times. In the center of Baku, this was probably like similar picture that you would see in this modern center of Baku. Actually, if I live not close to the Baku Higher Oil School building, the Khatay area, and every time there is new construction in this area and excavation works are carried out, I can see actually the mud underground, which is basically this oil that were stored on the surface in open reservoirs. During the second part of 19th century, the global demand for oil has increased as a result of industrial revolution and advancements in the engineering. Azerbaijan has actually become the #1 oil producer during that time. So our production was surpassing any other single country. We were making probably majority of the oil in the region, in the Russian Empire. The screen on the left-hand side, the photo on the left part of the screen is a refinery around Baku with the tanks. This is a little bit more modern because that's the beginning of the 20th century. The picture on the right-hand side that I put as a reference is two engineers from what is now called State Oil University, or before that used to be called AZI. And they have been pictured in front of the airplane, the actual working full model that they've engineered and constructed themselves. So Azerbaijan has actually gained a lot of advances in engineering because of the oil rush. So by mid 20th century, other countries has also caught up. So we were no longer the #1 producer of oil because there were much bigger reserves found elsewhere in the world, in Middle East, in the United States, in North Sea, Gulf of Mexico, and other areas. But still, Azerbaijan's rapid expansion had continued, and one of the engineering marvels of the world that we consider now, the Neftashtar was built, which is a set of offshore shallow water structures for oil extraction, storage, some processing. Have you guys seen the movie Fast and Furious 9? Anyone seen this movie?
Yes.
Yeah, so the top photo is from that movie. Actually, it shows the some of the structures, I think Neftashtar in sea. That is basically a reference to old oil infrastructure. So at this stage, it could be considered as something maybe historic. By the end of 20th century, there were more modern developments in the oil and gas industry in Azerbaijan. We already had oil refineries, 2 oil refineries that are still operating. One of them are being modernized, which will replace the other one, which is getting old. And in 1994, 20 September, the contract was signed with the international consortium led by BP on the development of the Azeri-Chirag Güneşli field, which basically is considered one of the key historic moments in the history of modern Azerbaijan, because it brought foreign investment. It resulted in development of the international major oil and gas export systems that are still making majority of the profits for our country. And this is basically, I think, also the day that we're celebrating as Oilman's Day, the day when the contract was signed. So today, this contract is actually, it was expired when it was, I think, 25 years old in, if I'm not mistaken, 2019. Please correct me if I'm wrong. But the extension contract was signed, so there's still multiple phases of this major development continuing. You can see from the schematic in the screen, there are series of offshore platforms in the shallow water Caspian Sea, from 60 to 70 kilometers to up to 200 kilometers from the shore. These include Deepwater Güneşli, Chirag, West Chirag, and Azeri platforms. And recently we're working on Azeri Central East project that will be another addition to this series of platforms. So some of these platforms, they have, for example, water injection, gas injection facilities. They have complex interconnected subsea systems, and there are export pipeline routes to Sangachal terminal. There are both oil and gas pipelines, actually multiple, that is connected to Sangachal terminal, and there's also produced water line from Sangachal to offshore. Sangachal terminal as well is a huge undertaking by its own. It's one of the biggest oil and gas combined platforms in the world. It's hosting not only the ACG that you can see on the screen, but also Shah Deniz developments, which is now Shah Deniz A and B platforms, and Shah Deniz side of Sangachal terminal plus Shah Deniz 2 terminal expansion. In the terminal, we've got oil treatment, oil separation and treatment facilities, condensate stabilization facilities, gas dew pointing facilities, and so on. On the left-hand picture, you can see the main export routes from Azerbaijan. We have one of the biggest ones is Baku-Tbilisi-Ceyhan pipeline. It connects Azerbaijan with Georgia and Turkey, and the endpoint is in the Mediterranean Sea, which gives access to products from Azerbaijan to the international market. There is also South Caucasian pipeline, SCP, which basically finished in the Midlands of Turkey and is routed basically at the same route. There are also expansions to the SCP pipeline. Some of them are already built directly to Europe. You can see on the right-hand side. So the gas produced from Azerbaijan, namely Shah Deniz fields, is sold to Georgia and Turkey through SCP. And with the expansion of Shah Deniz project with Shah Deniz 2, it will be, and TAP and TANAP extension pipelines, it will be routed to further down to Europe, to Italy, Greece, and so on. There are also some like older pipelines, for example, REP pipeline, Western Route pipeline. That is, it basically goes through the same route as BTC until Georgia, and in Georgia, it is routed to port in the Black Sea, in the city of Supsa. So I will be making references to the existing infrastructure that we have in terms of production and transportation, and how we can utilize this in the 21st century. So this is the current the split of production between different projects and reservoirs. It's not entirely up to date. I think it's based on 2015 data, but it's for a kind of reference. So you can see that majority of the gas is coming from Shah Deniz 1 field, and Shah Deniz 2 will be like a big contributor, almost doubling the country's gas potential. And there are a lot of smaller projects like Bulla, Ümit, Karabakh project, which is currently under development, that will increase the production. So if we look at the oil production worldwide, right now, Middle East is one of the biggest producers, and CIS is, which includes Azerbaijan, Russia, Kazakhstan, and some other former Soviet countries, is now much smaller contributor, and Azerbaijan is even like a smaller part of this. But the trend is that the oil demand and oil production has been growing ever since early 20th century, and there is no end seen to humanity's need for energy. In this chart, we can also compare production figures, oil production figures from 1980 and 2015. It's slightly, now it's probably slightly different to 2015, but it can be, for this purpose, can be regarded as relevant. So you can see that Azerbaijan is not even like listed as a country, because its share in the global market is probably less than 1%. And you can see that the former USSR used to be almost 20% producer, and now if you compare the recent chart, Russia is 11%, which means that other countries like former CIS countries like Kazakhstan and Azerbaijan are taking some of that share, but overall the production in this part of the world relatively is the relative share has reduced. So I want to talk about the global production of oil and how it's used. So this is figure from this figure is based on the US data. I use it because this is very nicely laid out and quite eye-opening. But it's I don't want to focus too much about numbers, because numbers will be different by year and by country. But the heuristics is that the oil is produced into different products, yeah, and so these different products are used in different sectors. So normally, when we talk about oil production, we think about cars and fuels to cars, but in reality, oil is used in many different for many different purposes, and obviously, um, the petrol for cars is one of the biggest use case for oil. Um, it's used over 40% of the oil is used to produce fuel for cars. And then we have got a distillate fuel oil, specialty um, fuels. We also have hydrocarbon gas liquids, for example, LPGs, um, which is used for different applications, not only for oil. And we've got others could be used for non-fuel and other sources like plastics and so on. And likewise, when we think about the usage of oil, that oil-based products, it's not only used for transportation, yeah, and actually transportation also does not only include cars, yeah. So there are aviation transportation, which is where jet fuel is used. We've got shipping industry, which is also like very big consumer of diesel, which is the fuel for most of the international freight ships. Industrial users are like, for example, diesel for plants or plastic manufacturers. And you can see that the residential and commercial is one of the smallest users of oil-based products. What is notable to also see that, for example, transportation, yeah, it uses not only motor gasoline, basically petrol, it uses all sorts of products from oil, and that is why we have such a big variety of fuel type products from oil, is because of the use case. Something that you can use for jet engine is not good for example, a car. So we have to have fuels with different properties that are suitable for different applications. And when we talk about transition engineering, we'll have basically similar type of chart where we have sources and we have got usage sectors, but the sources will also be not necessarily products. It could be electrical energy, it could be hydrogen, could be anything. And sectors will also change based on the offer from the energy market. So if the previous chart, we've looked only at the oil production, the global oil production, but this one of the main things that we use fossil fuels, namely gas, is for electricity production. And electricity can be produced in many different ways. And you can see in this chart how the share of each source of electricity has changed over years. So one big trend is that overall basic electricity production has increased at a rate very similar to oil production, and that is because of the advancement of the civilization after industrial revolution. We all have more better lifestyles. We have cars, air conditioners, and so on, hygiene. So we need more energy to sustain our modern life. Um, Still, one of the biggest sources of energy for electricity production is coal. The problem with coal is that it's not the exhaust from the coal burning plants is quite bad for the environment, and therefore there has been a lot of push against coal, which has resulted in the increase in the gas consumption for electricity production. Um, we also have quite significant renewable share in the electricity production, and biggest is hydropower. But hydropower is limited by the geology, by nature. So there is certain limit that we can produce with hydropower, but wind and solar are increased. The production is increasing at fastest rate compared to any other source of energy that you can see from the bottom. So in last 10 years, the production from wind and solar has increased multiple times, much more than, for example, the rate of increase for gas or hydropower. And it is expected that due to advancements in technology, as well as mass scale, um, uh, increase in wind and solar is going to be exponential. Okay, so if we have got, now you may ask that if we have got renewable energy, then um, uh, we have some balance. We've got renewable energy, we've got fossil fuels based energy. So why don't we just continue? Yeah, you as students, you graduate universities, join these companies, and continue doing whatever your predecessor was doing. So why are we even talking about this in such a passionate way? So one of the main problems that actually is not found now, it's been known for decades, but has been exacerbated now, is the climate change problem. So as a result of usage of hydrocarbon-based fuels, we are emitting carbon dioxide. We're also emitting other gases, but carbon dioxide in much larger quantities. And this resulted in increase in carbon dioxide concentrations at unprecedented levels. So you can see from the graph, it shows us the timeline that it's even hard to imagine. Yeah, this is, for example, 800,000 years. You can see that we can trace back. We have got samples in ice that trapped air and other samples that we can quite accurately measure the composition of air in such ancient times. And we now know what the timeline of carbon dioxide concentration is, and we know that this level increase has never been seen before. You can see that the right side of the graph um, is the increase is so high that at this scale, it's almost like a vertical move. So we've almost like jumped our carbon dioxide concentrations in like 1 millisecond. Actually, it's 100 year, but 100 years, doubling the carbon dioxide concentration in 100 years is extremely fast move for our fragile Earth, which has evolved thousands of years to this state. And the problem with carbon dioxide is that it acts as a greenhouse gas, along with other gases like water and, for example, methane. And it makes atmosphere accumulate more energy, and hence change the temperature or average temperatures of our planet. So apart from that, because we already have some renewables, yeah. So then one of the first to do is to use renewables for everything, yeah. So why don't we just stop producing fossil fuels and switch to renewable energy? Yeah. First of all, we don't have so much renewable installed capacity to continue living the same lifestyle um, uh, with our current energy needs. But even if we had, let's say that we have got like 100 times more installed renewable energy. Can we actually forget about fossil fuels? To answer to these questions, I want to offer you to look at the chart on the left-hand side. This is basically, it's a sample. It doesn't represent any specific location or case, but it's almost like worldwide is the same shape that you will observe. So during the day, we have got varying energy uses. Yeah, so we've got peak at around like 5 o'clock, 5 p.m. And when we sleep at night, there is very little demand. So our energy demand changes based on the time of the day. Yeah, but it also changes based on the time of the year, and it changes based on multiple other factors. But this basic regular like change uh, means that we have to have energy available when we need it, not just whenever it can be produced. And the problem with the renewable energy is that it's intermittent and it's not controlled. Yeah. So uh, when there's, for example, no wind, there's no energy produced from wind. That's why actually I brought up the case of Germany, because Germany has got a nice like spread of all types of sources for its electricity generation, and you can see that wind is very significant part of their energy mix for electricity. And I know that this summer in August and July, they had very calm days where there was almost no wind. So imagine that if Germany had like total wind based electricity production, they would have basically total blackout due to the changes in the weather, due to low wind speeds and lack of wind in most places. Um, so we can't basically 100% rely on renewable energy right now. So right now, fossil fuel-based energies like um, um, like natural gas is used as a buffer energy source. So when there is less wind or more or less sunny days and when the production is less, we cover it up by using more or less hydrocarbon-based fuels, because we can store them and we can increase or reduce production with them as we want, because it's controllable, storable energy, which is not the case with the renewable energy. So with these two problems in mind, specifically with the climate problem, the countries all over the world has gathered in multiple forums in Paris Agreement and multiple other binding agreements in the international agreements. They've committed to reduction in uh, carbon emissions to a certain level. So every country has some sort of plan to, most countries have some sort of plan to reduce their carbon emissions by 2030, 35, and 50. In case of Azerbaijan, we have got right now renewable energy is only 17% of the total energy mix, and sorry, 22%, yeah, increase from last year's to 17% figure. These figures are, I've taken this from the presentation from the Ministry of Energy of Azerbaijan, and the plan for the short-term plan that is available for me right now is 30% um, uh, reduction to 30% by 2030, which is not as aggressive as some of the developed countries. But we should also bear in mind that Azerbaijan is not a huge energy consumer. Our energy consumption rate is still below the global average per person, I mean per capita, and much lower probably compared to developed countries. Um, so we can perhaps reduce our own emissions relatively easily. But the problem is that we're also producing a lot of hydrocarbons that will be causing carbon dioxide emissions elsewhere. So the gas and oil that we've sell to Europe and elsewhere is going to be burned somewhere and cause carbon dioxide emissions. But still, we have to also make our share of contribution to the carbon transition. We have remarkably, we have a lot of potential, probably enough potential to have 100% renewables. We've got 300 megawatts of wind capacity. We've got 23 gigawatts of solar capacity. We have got even biocapacity and hydro capacity. We already have. So the current, unfortunately, I don't have we have got the information. So if you look at the pie chart, you can see that majority of our renewable energy is coming from the hydro plants. We also have got some potential in the recently liberated regions around Karabakh. We also have got geothermal potential in that regions. So what can we do? How we can how we can achieve net zero? As engineers, as chemical engineers, there are multiple ways that we can contribute to this, to those. Blue, green ammonia. So ammonia is already used as a is very important material for food production, for fertilizer production. We can also produce ammonia from renewable sources and use it as either directly as energy or convert it to hydrogen and use it as a green hydrogen source, either at fuel cells or by combusting it in industrial processes. Carbon capture, storage, and utilization is not a very popular and support is not favorite thing that Greenpeace would like, but unfortunately we can't transition to renewables overnight, so it will need a lot of hard work and time. So, and we will still need to continue our good lifestyle, so we have to have energy, which is right now mostly available in fossil fuel forms. But as we continue to use fossil fuels, we can try and make it less damaging to the environment. We can capture carbon dioxide that are produced in the processes, for example, in combustion processes, in gas plants, or in chemical production processes. There are also some developments for capturing carbon dioxide directly from air. There is recently there was an announcement of the carbon capture plant in Iceland by a Swiss company, so that they are using geothermal energy that is abundant in Iceland to drive this plant, and they're directly capturing carbon from the air, which is equivalent to, I think, 1,000 cars of emission, which shows, and this project is basically the biggest plant of such kind ever produced, and it shows that how little this technology will do. But industrial carbon capture and storage is at much higher scale. The amount of carbon that can be captured from the power plants, from chemical plants, is huge, and it can be done with relatively quickly. Then we have kind of alternative energy source of hydrogen, which is by its own is not an energy source, because we don't have hydrogen in its free form in nature. So we have to produce hydrogen somehow, which makes it less useful, because we want to gain energy, but we have to spend energy to produce something. But hydrogen is something that is very clean to burn, and it can be stored, but there is a lot of problems of storing and transporting hydrogen. We'll talk about them later. These are all interesting challenges that hopefully some of you will be working on in your later careers. Decarbonization of existing assets. There are a lot of projects right now that look at the existing assets, how they can use less energy, how, for example, oil production facilities can do less flaring and emit less methane and carbon dioxide, how energy integration and recovery systems can be used to be more energy efficient and use less energy and less gas to be burned to energy production. Um, we can engineer products that will reduce the need to raw materials. Yeah, for example, by building materials that can be used multiple times. Yeah, um, and making them more recyclable. So a lot of plastics are very difficult to recycle because they are designed to be produced cheaply, but we can engineer plastic materials that can be also recycled more easily. We can also try to use more recyclable materials in our designs. For example, aluminum is very easy to recycle. Renewable biofuels is also has good potential, as well as in Azerbaijan. We have got straw and other sources of biofuels that can um, be either used as standalone or can be mixed with fossil fuels, um, and many countries are already doing this. And renewable and integration of renewable energies. So we are at the stage that even for fossil projects like oil and gas projects, we are considering renewable electricity sources, not just because of environmentally friendliness, but also because overall feasibility. Sometimes it's much easier to produce clean electricity from the shore and supply it to the, for example, platform or the plant, than to burn the valuable gas to produce energy at the plant. Now I want to talk about hydrogen. Are there any questions?
Yes, actually, we have a question in the chat.
Yes.
Isa asks that.
Mhm.
Isa asks that with the rise of EV, the importance of fossil fuels will be diminished for transportation. From your perspective, how will the oil and gas prices will be affected?
Thank you for asking the question. I think it's a very good question. First of all, well, fossil fuel production has to be reduced anyway, yeah, and because of the climate reasons that we've discussed, we want to use more clean fuels, but we'll have to use fossil fuels during the transition, yeah. But the question about the price is quite difficult to it's quite difficult to predict now, because we are trying to bringing legislation that will make us use and produce less oil. Yeah, not just because of EVs. Yeah, EVs are also remember that EVs are also right now subsidized. So companies or governments are putting money, investing money so that people buy electric vehicles, and companies build the electric vehicles. Um, um, so in order for um, um, the EVs and building, manufacturing, and owning EVs to be feasible, the price of the fossil fuels has to increase. Yeah, because otherwise EVs will be less and less affordable for many people. So average price for electric vehicle right now, even the cheapest one, is much more expensive than the fuel fossil fuel based, because it's fossil fuels cars are at end of their development, so they are very mature industry. So it's very difficult to compete for EV industry. But the price is something that will not be determined by the free market. So we'll have to make some policies. We have to make some regulations. We have to make some incentives to regulate the oil price and fossil fuel based products price, so that it makes sense for the consumer to transition to greener electricity, which is right now more expensive. I don't know if I have answered your question, but it's a very interesting question. I don't think we have got the answer now, but I think the price will cannot go down dramatically. Yeah? Otherwise, it will be uncompetitive for EVs and other electricity users, green electricity users.
Thank you for the answer. Also, Issa, thank you for the answer. He wrote in the chat.
Thank you. Then before diving into details of hydrogen and why we need it, let's talk about what the types of hydrogen. Basically, these are all the same hydrogen. It's only the way they have produced it, which is basically the most important part, yeah, because we want to transition to hydrogen so that our carbon emissions are reduced, yeah. But there's a lot of kind of misinterpretation of hydrogen being green energy source. Producing hydrogen is not green source at all, you know, if you're not using green electricity for its production. So to simplify this, there is color scheme devoted to hydrogen. So green hydrogen is what we usually refer to when we talk about hydrogen as electricity, as a source of energy, because otherwise the current hydrogen production is basically fossil fuel based, which is gray hydrogen. So gray hydrogen is even worse than directly burning fossil fuels, because but the unit of hydrogen will give you less unit of energy than directly burning gas, for example, yeah, because you have to spend more energy to convert this gas to hydrogen, and on your way you will also have carbon emissions. So it's not, so gray hydrogen is something that we don't want at all, yeah. And green hydrogen is the ideal case, is what we want, is hydrogen produced from primarily water by electrolysis, and the energy, electricity for electrolysis is coming from the renewable sources such as wind and solar. So the one problem that it solves is the intermittency issue of the wind and solar, because as there is wind and solar energy, you can produce more or less hydrogen, and you can somehow store it, which we'll talk about later. The most interesting controversial part is blue hydrogen. Blue hydrogen is basically hydrogen that is produced from fossil fuels, like gray hydrogen by steam methane reforming or auto reforming. But when we produce gray hydrogen, we also produce carbon dioxide. So if we capture and store this or use this carbon dioxide, then we don't, this hydrogen basically is cleaner, yeah, because it's causing less emissions. So one problem with that is that the natural gas production itself is quite environmentally unfriendly, and there are a lot of other emissions on the route. Actually, there was a international paper published recently on this subject that discusses how clean is blue hydrogen. So the consensus is not, I think it is not reached on the blue hydrogen, whether it has a role to play or not. But regardless, we have a lot of blue hydrogen projects on the pipeline around the globe, and it is part of hydrogen strategy for multiple countries, for example, like UK, Japan. So whether we want or not, blue hydrogen will need to be produced. So our hydrogen transition will be dual path, where we have green hydrogen and also blue hydrogen until we reach 100% clean hydrogen, green hydrogen. Turkish hydrogen is relatively new technology where hydrogen is produced, and instead of when we produce hydrogen from methane with pyrolysis, unlike, for example, SMR or outer reforming, we don't get carbon as in gas form, but solid carbon, which is already separated and not emitted to atmosphere and can be easily used. Pink hydrogen is also quite clean, but it's produced using nuclear power, which is not the most safest and healthiest ways. Then we also have purple hydrogen, which is basically co-gasification with carbon capture. So out of this, we should mostly concentrate on blue hydrogen and green hydrogen, and ideally we should try to produce only green hydrogen. Okay, so hydrogen is quite different from oil, and when we talked about oil, we talked about the different types of fuels that can be made with oil, from jet fuels to high octane gasoline fuels. So we can produce various energy carriers at very high densities. Although hydrogen has got very high density per mass, but its volumetric density is very low, even compared to natural gas, for example. It's 3 times less dense than natural gas, which creates a challenge for transporting it in gas form, like we would the natural gas, for example. Yeah. So, for example, if we were to use South Caucasian pipeline to transport hydrogen, then with all the other conditions the same, we would probably be able to transport 3 times less hydrogen. So we have to think about how we use hydrogen and where the hydrogen is set best. Yeah. So different countries have different basically predictions about hydrogen and goals about hydrogen. For example, by 2030, Germany, Japan, and Korea will have 1 hydrogen out of every 12 new cars produced. So that is a huge change for example, the personal car industry. Whereas right now there is mostly only 1 company that produces hydrogen fuel cell based passenger car, Toyota HFC, I think it's called, which is not very popular car at all. So not only the users and applications, we also need a network of transportation. And Europe is planning now almost 40,000 kilometers of hydrogen pipelines by 2040. So 30% of them will be new pipelines purpose built for hydrogen transportation, and 70% is repurposed natural gas pipelines. So repurposing natural gas pipeline is also quite challenging task, because hydrogen has immersion to metals. It can leak much more easily, and detecting it is different compared to, for example, natural gas. So there are safety and engineering challenges for producing um, hydrogen, but there is also interesting proposition about um, clean energy storage and transportation. Remember that natural gas pipelines themselves also provide some buffer um, for uh, storage. Yeah, because for example, South Caucasian pipeline is almost like 1,000 kilometers long. Yeah, so it would contain tons of natural gas at any given time. So even if there is some shutdown or outage, there will be uh, um, um, some capacity in the pipeline for some time, yeah, which is in oil industry it's called line packing. So there are a lot of major projects being planned for hydrogen production, and we as a country, as a historically oil producing country, can also utilize existing infrastructure to produce hydrogen and sell it in the global market. For example, SCP pipeline, TAP and TANAP add-ons can be used to transport hydrogen. As I said, the hydrogen capacities of these pipelines will be much reduced. But as Europe also is transitioning to cleaner energy, their demand for oil and gas will also reduce, yeah, 2040 and moving on. So one way for us to get prepared is to switch to producing something else, because Azerbaijan is heavily dependent on oil and oil-related exports. It's actually making 90% of our, more than 90% of our economy. So if oil is not needed or demand is reduced by 2040 as expected, this will have huge implications to our economy. So we have to have some replacement plan for our current energy industry. So where is hydrogen used? So right now, hydrogen is primarily used for ammonia production and in refining processes. Yeah, in refining, we use it for hydrogenation to produce, for example, specific oils. Um, and ammonia is used to produce fertilizers for food industry mostly. But if you look at the projection for 2050, you can see that hydrogen will be used in all new fields, like for example, transportation. That is gray area on this bar chart, which is by its own, it's bigger than um, hydrogen used for ammonia production and for refining process. So in addition, we'll be using hydrogen for buildings, basically heat as a house heating. We'll use hydrogen for synthetic fuel production, um, and as well as the existing usage cases for ammonia and refining. So if we've got so many possible ways to use hydrogen, and if hydrogen production is not so easy, we have now challenge of the how we should use this limited source of hydrogen, which we haven't even yet produced. Yeah, but if when we produce it, we won't have hydrogen uh, to power everything. So um, Michael Liebrich is author of this nice chart that I like to refer. So he's basically um, shown a ladder for like in energy efficiency. Like for example, if you want to buy a house appliance, you would see that this house appliance is rated for a certain energy efficiency category. The same, if we apply the same principle for hydrogen and where it's best used to achieve highest results, the A ladder is fertilizers, because we're already producing hydrogen gray hydrogen, dirty hydrogen, by emitting a lot of carbon dioxide to produce fertilizers. So his argument is that if we are already producing hydrogen by emitting a lot of carbon dioxide, why not just change the source of that hydrogen first? So if we have produced hydrogen, instead of creating green hydrogen, if instead of creating users, fuel cells, filling stations, and so on, we already have fertilizer plants that are using hydrogen. Um, the same with methanol and refineries. So these are the users that already are using gray hydrogen that needs to be replaced highest priority. Then we can use it as for producing aviation e-fuel, shipping e-fuel, and steel. Why the e-fuel is because hydrogen is quite challenging to use as a fuel due to the volumetric energy density, which is very important in aviation and shipping. Then we can use it for long distance trains and power systems backup, which is basically the energy storage solution. Industrial heat and long distance trucks are also good alternative because they are very difficult to, for example, long distance trucks, they are very difficult to switch to electric vehicles because the power, the battery pack size will be huge. It will be very expensive to produce such large battery packs, and it will take long times to refill. And then we can start using hydrogen for heating commercial buildings, for producing electricity for island grids. And then the last two ladders are mid-distance trucks and domestic heating. So the reason mid-distance trucks are lower rated trucks is because mid-distance trucks, they don't need much of a range and much battery capacity. There are already companies that are producing some sort of like low range mid distance trucks. So there's no need to transition it to hydrogen, or less need to transition to hydrogen. The same with domestic heating. Domestic heating actually can be achieved without any combustion. For example, with good insulation and electric heat pumps. So using hydrogen to as a heat source for domestic use is not huge improvement. Actually, it's I would say it's even worse in terms of safety than, for example, natural gas. Hydrogen fuel cell cars, again, because personal cars, they don't have to have huge range, and we already have history with electric cars. We know that it's possible to have low to mid-range electric cars. Yes, they are expensive now, but they will become cheaper, and they are overall cheaper to run if you also factor in the energy costs. So that, and we already have targets for car manufacturers to produce electric cars, so there's no need to transition them to hydrogen. Same with the urban delivery low distance vehicles.
Rafat, I can ask a question.
Yeah.
What is e-fuel and synthetic fuel?
It's basically the same thing. What I refer synthetic fuel. Yeah, in some places it's referred to as synthetic fuels, some places as e-fuel.
Okay, thank you.
Basically the fuels that we are manufacturing ourselves here, rather than like fossil extracting it from the fossils.
Understood. Thank you very much.
So I've already discussed a little bit about the challenges with hydrogen. Hydrogen is transporting hydrogen is much more difficult compared to, for example, petrol, yeah, which is in liquid state. It's very high energy density. You don't have to pressurize it, but the case with hydrogen is different because it's in gas form. You have to if you want to keep it in a gas form, you have to compress it. So if you compress it, you have to have high pressure rated equipment to store it. Even then, its energy density will be much lower than, for example, liquid hydrocarbons. So how do we tackle this? One way is to liquefy hydrogen. Yeah. So hydrogen liquefaction is already uh, used in space industry. Yeah. So um, but the space industry is not the most like energy efficient or the cheapest low cost industries. So the cost of fuel, storage, and transportation for example, International Space Station or rocket is not significant because it's already like very expensive undertaking. Um, but the technology is relatively simple. We um, um, we are cooling down uh, um, hydrogen, if I'm not mistaken, up to minus 180 degrees C to keep it in liquid state. Um, and then we'll need like specific materials that will be able to keep their properties at that low temperatures. And when we want to utilize it, because we can't burn like cryogenic liquid hydrogen, we have to use gasification. This would be very similar to the LNG industry, which is already doing this. So we have um, uh, natural gas plants, for example, in Nigeria. We liquefy the natural gas in Nigeria and ship it via LNG tankers to every part of the world. So the same can be done with hydrogen, except this will be even more challenging because hydrogen will need even lower temperatures, and also storing it is costly. It's not something that you can produce and store. So in order to store it, you have to make sure that um, you're maintaining the temperature, or you have to basically um, manage your boil of gas, because there will be heat transfer from the atmosphere. Um, um, and this heat transfer will be even higher due to the lower temperatures, the bigger temperature difference. So some of the hydrogen will be vaporizing. So you'll have to have some boil of gas utilization system. Another, so this is basically new information that we have. This was published in the KBR Hydrogen Energy Carrier white paper, which is available online. You can also find it out and download and read it. Another new method for hydrogen carrier is basically liquid organic carrier. This particular one that I have information about is methyl cyclohexane. So hydrogen, green hydrogen, is reacted with toluene to produce methyl cyclohexane, which is in liquid form. So it will have much higher energy density compared to gas hydrogen. And in liquid form, it can be transported, for example, in pipelines or in tankers to where you need to utilize. And you can again have the reverse reaction and apply some heat and energy and produce toluene and hydrogen. So toluene will can be reused again to generate more MCH. Um, so this is not a commercially ready process. It has been tested at pilot scale, but sorry, it is claimed to be commercial ready, but hasn't been used at industrial scale. And note that we have to apply heat to basically split MCH into hydrogen and toluene. And we will need to take off the heat when we are trying to react toluene with hydrogen when we're hydrogenating. So uh, both so we have to either have some sort of energy integration, or we have to lose energy in both cases. which makes hydrogen, which is already kind of very low efficiency because we've lost a lot of green electricity that we used for hydrogen production, and then we have to lose even more to convert it to some type of like organic carrier. And then the last option is to use ammonia as a hydrogen carrier. The same way we're using the same, we are going to continue the way we're producing hydrogen by by reacting nitrogen with hydrogen, and in this case we're going to use green hydrogen. But instead of using ammonia for producing fertilizer, we can use it for carrying hydrogen. And for example, we can produce green ammonia in Japan, ship it to Australia, and in Australia we can have dehydrogenation plant and produce hydrogen. So the benefit of this technology is that ammonia production part is already in place. So there are ammonia plants that can be converted to using green hydrogen, but the dehydrogenation part needs to be uh, developed. Yeah, and if technology moves on, I think some of the oil pipelines, for example, like the one, for example, PTC1, can be converted to carry ammonia. But again, this is not a plug and play type of transition. It has to be re-engineered for this purpose. So that is actually the end of my presentation. In summary, I want to um, share my own like views about the future and the current state of energy industry. Um, so the job for engineers is going to be much more diverse in the future. Um, Maybe 20 years ago or 10 years ago, if you graduated university, you would know that you would most likely be working on oil company or some engineering company that is contracted by this oil company to build some sort of oil producing facility, oil producing or refining facility. Right now, there are a lot of works and a lot of engineering analysis, a lot of development in new different areas that have never been explored before. So this is creating a very interesting prospects for um, the students um, and future engineers, and there is no substitute for oil as we would like it to know. So if yes, we are going to use produce we will have to produce less oil and gas. Yes, we will have to use more renewables, um, but we still have to continue to sensibly use oil and gas, and we'll have to engineer different energy systems for producing and using energy.